Welcome to the actually first session of the day, and I'm happy to be here. I'm sorry that I don't really know French. I wish I could say something. I can fake saying bonjour. That's all. And so today we will talk about the locking in Postgres, how the lock queue works, and MVCC a little bit, and then mainly about DDL locking and how we can actually reduce the lock contention. That will be the main part of the talk. And then at the end, I will introduce an open source tool that we develop in the company that I work for to introduce you a way of handling zero downtime schema migrations. And that's me. Who am I? I work at a small startup called Xata. We work remotely from different parts of Europe, a relatively small startup. And I got recently recognized as, I don't know what happened, but seems like I got lost there. You hear me? Okay, okay. So I got recognized as a Postgres contributor. I didn't contribute as a code contributor, but I am running several meetups and part of the call for paper committees and I don't know, volunteering, and I was also part of Postgres Europe board at some point. So like for the Postgres community, I think I'm working professionally with Postgres over 12, 13 years now, and at that long I am part of the community and happy to be here still. And yeah, I live in Prague, and if you ever visit Prague, or if you want to have a reason to visit Prague, we are hosting Prague Postgres Meetup. I'm hosting it. So if you have an idea, want to visit, contact me, and I'm happy to have people, coming over to just, see the Prague and also have the meetup. And I am originally from Turkey, and I run an organization over 10 years called Gulcin Yildirim JELINEK. It literally translates as Women Devs in Turkish, and we have our own conference now today. This year we will have it in July, third time. It will be about AI, but we also do other events. So that's enough about me. Let's continue. And this is my first time in Mons, and I don't know how many of you exactly from Mons. Is there anybody who is local? Yeah? And mainly like how many Paris? I think Paris is like a lot of people from Paris. Okay. Where else? I don't know much. I know Brussels. Yeah. But I liked yesterday, since it was mainly French speaking, so I went to sightseeing, went to the Fine Art Museum. If you haven't been, I recommend it. They have a really nice garden. And I seen Lucy and the butterfly, so happy to be here. I enjoyed the city, and I think I got lucky with the weather too. Yesterday was good. And agenda. So first we will start with the MVCC architecture. We will continue with the DDL locking, what type of log modes available, how they interact with each other, how can we avoid access exclusive logs. And then we will talk about the log queue in Postgres and how we can reduce the locking impact, how can we reduce the log contention, and at the end, pgroll, as I said before. So what are logs? When I was planning to kind of prepare for this talk, I just thought, okay, I will have to do something because I got involved in the project, pgroll project, and the whole point of the project is to minimize locking so that you don't cause downtime when you do the schema changes. So I was like, okay, so I need to explain people, or I mean, at least work around the topic that actually correlates with it, so locking in general with DDL. But I go to the topics as like very wide and general perspective, so I go like, okay, I will talk about logs. So I bought books about like literal logs, like history of locking, Persian logs, how to do log picking, because it's a way of procrastination, right? And also like I'm researching about the logs. But then I come up with something that, either it is like real world or in Postgres world. In real world, logs are usually about security, right? You can secure a safe or door or something. But in Postgres, it's nothing for security. It's not a concept for security. It's about concurrency. So that's one thing to, not associate with actually physical logs. But there's one thing that I can actually correlate these two concepts of like, real world physical logs and Postgres logs. To be able to pick a log, you need to understand its pins, its tumbler, the mechanism that how it works. And if you just manipulate these things, you can actually open a safe or a log without actually having the key. So to be able to understand same concept like locking in Postgres, you need to understand some under mechanisms, basically, like about concurrency, how it works. That's why we will talk about MVCC, because if we understand these concepts, how the transaction isolation works, how MVCC works, we can actually understand logs and log contention and log queue as well. Okay, so how does actually Postgres handle mainly the concurrency issue? So we have the MVCC for it, mainly for DML. And MVCC is not specific to Postgres only. It's like many databases use it, different softwares use it. But in short, like when we hear about MVCC, it means like we are writing new copies of data rather than modifying the rows in place. That's one thing. And then that ensures that reads don't block writes and writes don't block reads. So this is the mechanism for Postgres that it makes it really efficient for the concurrent DML, like kind of data manipulation operations. So we just like, since we keep creating different copies, we are actually allowing reads and writes happening without blocking each other, which is perfect. But even in this MVCC-based system that we are having in Postgres, we still cannot avoid some degree of locking, basically. And they will, like reads will still acquire lightweight locks, and it will be like, it will require these locks in tables and views, all these data types, database objects, basically. So we cannot solve everything with MVCC, but it solves like most of the problems that come with concurrency, but it doesn't still, we cannot avoid taking locks to some degree. And so when we talk about MVCC, I know probably everybody already knows what it is, but I wanted to show you an example, a simple example to illustrate how actually it works. So let's imagine in this example that I created here, there is a single row at the first row. So I divided the columns like transaction ID 100, transaction ID 101, and this is what happens when I actually see those things. So first thing maybe to say, what are these things that I post here? In in Postgres, there are like system columns that are called like xmin and xmax. These are not visible to users, but it is kind of crucial for how MVCC operates. And if you know this too, you will already know a lot about the system. So xmin is the transaction ID that creates that version of the row that we are currently seeing. And xmax is the transaction ID that deletes or updates that version. And if it's null, it means it's current. And there are other things like cmin, cmax. These are like I think how the command IDs within the same transaction, or there's like physical location of the rows and so on. So, but you can actually get by a lot with xmin and xmax. So this example also, to kind of, as a disclaimer before we start, it is displaying the behavior, default behavior of Postgres, because in Postgres we have different levels of transaction isolation levels. And this is the default one, and it's called read committed. So if you do this example in different versions of the transaction isolation levels, you will not see the same results. So this is what I'm displaying as the Postgres current default behavior. Okay, so let's see. And there's like first row, you can see there is Alice's salary. We are just like selecting from Alice's salary, that query. It shows it. It is at 50,000. And the first transaction, this is transaction 100, it starts. When it starts, it gets a snapshot for the select statement. And so it sees the salary of Alice at 50,000 because the xmax of the row is null, means that this is the current one. And the xmin of the row, previously you could see, it is 99. So it means that there was already, it is less than our current transaction ID, so we can see it. It's already committed before, so I can see that. And then the second transaction ID, it comes, transaction 2 is like 101. It updates the salary to 60,000. So normally, if we didn't have the MVCC, we would do the update of this value in place, but we don't do that. So we create another version. This time, we have like a version with 50,000 and a version with the 60,000. So old version is the 50,000 one. The old one, we mark it with xmax 101 because that is the transaction actually affected this, right? So we mark it that 101 actually affected this, we updated this value, and the new version is created. And this time, since it is the 101 is creating this version, the xmin is the 101. So we can see that what's happening literally. And once the second transaction, this update transaction commits, then the new snapshots will actually see this value. But until it commits, when I have the second time I'm acquiring the salary again, I will still see the 50,000 because the transaction ID didn't commit yet. And up until that, in this behavior, we will still keep seeing 50,000. But once it is actually third select comes again, asking the same salary, and then I can see the 60,000 because it gets a fresh snapshot, and it actually is the behavior after the commit. So I can see that like transaction 101 is committed, the raw version with xmax 101 is the current version, and xmax is null because of that. And then I don't see anymore, it's not anymore visible. It's no longer visible. If the old version now that xmax marked with 101 means that new transactions will not now see this 50,000 anymore. Basically, this is how it works. And what you can see here, like, okay, MVCC sorted this issue. We kept actually offering, we solved this like concurrency problem maybe that would occur without it. But then there's always some cost with every decision. For this time, we can have like these dead row versions accumulating because we still keep those things, even though it's not visible to the new snapshots, but they will still keep accumulating. So we call this dead rows, right? And until it's cleaned by a vacuum process, we will just keep it. So that means that we can actually temporarily grow the size of the database because we are keeping the multiple versions. That is why it is really essential to, vacuum maintenance is important. So you need to make sure that you tune your auto vacuum settings properly. But again, I don't want to end it in the negative note. Basically, thanks to this, Postgres can provide consistent snapshots for any long-running query. Hopefully, they will not run too long. We will see why it's not a good idea to keep your transactions running too long. But thanks to this, we can actually still provide, if there is a, let's say, query getting that previous version of this row, they can still operate it while we can actually keep updated the value, and we can just still operate in the high read-write workloads, basically. Okay, so if it's all like, why do we actually log? Because like it doesn't really seem to have a like clear benefit at first sight, because it will definitely reduce the throughput. It will potentially increase the latency. That means it will be a kind of loss of performance while we do all this logging. But the whole reason behind is that we actually make sure that data doesn't have corruption and everyone is getting a correct result at the time of their query. And to be able to achieve it, we have to have this agreement that, when multiple transactions targeting the same resource, I have to make sure that I take some time and I offer the correct results at the correct time. Otherwise, it will be super fast. We could offer wrong results and people can see all sorts of concurrency anomalies, and that's why we are trying to avoid it. That's why we are actually locking. And if you think about the two extremes, imagine that we don't lock anything and versus we lock everything, like everything operates at one time, and for a query that's one query we are blocking all the table or something, that will be a hell. And in the real life, we don't really have this possibility anymore. We can't really imagine one user using one system so that we can actually lock all the resources. But we have to basically come up with ways to kind of combine these two extremes and make it make sense. So that's why we have the isolation levels as we talk, and you can actually offer, like there is read uncommitted, read committed, something more, and then serializable. So there are different degrees based on how much of this you want, how much of this lock you can take, and how much of security you really, really care about these operations, basically, how much you prefer to see your data, how do you prefer processing it. Okay, but today we will mainly, as I said, talk about DDLs. Why? Because DDLs are something I think everybody has to do. When you create a database, you don't really think that it is a static thing. It will never change. I created this table with this specific column, this specific constraint, this specific index, and I will never ever touch it. It's not really like that. It's like these are like kind of living things, like they get mature. You sometimes don't use some parts of it anymore. You need to drop a column, or sometimes you have to evolve this schema, totally different thing. So you have to understand the implications of DDL, because these operations you can't really avoid. And it is not really maybe the most often things that happens in the databases, but when it happens, it has big implications, especially most of them taking high level, like most restrictive logs. We have to understand how to make this safer in the operating way. So again, like why? Because they almost always need the stronger logs. It's like when you do an alter table or a vacuum full, you will probably take the stronger log. And they are not only blocking other DDL commands. Like when you run a DDL command, it's not only blocking the other DDL commands, but it can actually block your DML commands, like all these updates and merge and everything. Or they can even block select. So it means that they can actually stop all the access, all the concurrent access to a very critical table, let's say, and you're in production, you don't want that. So you need to find ways to reduce this locking time or the locking degree, or ideally both, so that to plan your migrations to cater these needs. And there's also like fine details. Basically, not every alter command taking the same level of, same degree of log. So some subcommands have different degree of log. So it's really kind of gets like more detailed once you actually look into it. And I divided the presentation for this like small snippets of information. So if you don't take anything from today, you just take these things with you. There's like 5 or 6 of them, easy and digestible information bits. So the first one is that to get to know and appreciate maybe, MVCC protects you from writes blocking reads and reads blocking writes, but it will not actually stop the reads taking logs. And there are different variants of the same commands, and some subcommands are different too, so you need to understand what happens in your database. Okay, so I kept talking about the logs and logs and logs, but we didn't see what do I mean by log mode. So this is from Postgres documentation. From top to bottom, the more you go down, the more restrictive the logs get. So the one that we are trying to literally avoid the most is the access exclusive, because the first one is like really simple. Let's say it starts from, this is the most basic log at the top one, access share. It's used by select operations, so multiple transactions can hold this, and it could be like simultaneously hold, and it's the least restrictive. And then you go lower and lower. I think I marked this like kind of purplish pink to show that where actually DDL area, DDL zone starts, but before there is like DML, operations saving row exclusive and so on. But the more you go down, they interact with each other, they block probably each other. And there's one thing is very important to understand which commands take what log, but another thing is actually, I think, maybe more important, how these logs interact with each other. Because to understand this comparison, there's a matrix in Postgres documentation as well. I recommend you to check that because, I don't know, for example, share update exclusive, it's actually conflicting with share log, share row exclusive, exclusive log, and access exclusive log. So to be able to understand how these things interact with each other, you need to really know this matrix, basically. And the last one, as I said, access exclusive. It is the most strong one. It can be used by like drop table, truncate, most of the alter table, vacuum full. It blocks everything. All concurrent access is blocked, and it is mainly required for schema modifications. That's why we will talk about it today. Okay, as I said, it's very important, like how these different log modes interact with each other, and access exclusive really conflicts with everything. With selects too. That is really hard to grasp because you don't really think that something can actually block your selects easily. So this is something that needs to be, focused about it. And of course, Postgres is like not stupid, right? It's really smart. So if it can take maybe a log that is less restrictive, it will take it. There are optimizations to make sure that we are actually taking the most optimal and efficient path. But there are some things you can't really avoid. So for some operations, you have to take that access exclusive and for that duration. But there are ways that we will actually see in the presentation with the real queries, how we can make things a bit better. And in the last item that is really important, and we will talk it in the next takeaway, is really crucial. Imagine once a transaction, it took a strong log, and it will hold this log until the whole transaction ends. So if you are mixing in the same transaction a table alteration and data manipulation, even though for data manipulation, let's say for your update, you don't really need access exclusive, you could just do it fine with row exclusive, but since you took this like access exclusive for the transaction in the alteration part, it will take the whole time for needlessly holding the most restrictive log. And so you need to be very careful when you are mixing this command. So the best practice, which will bring us to takeaway 2, separate, don't mix these commands. If you avoid it, like if this is a strong log requiring operation, let's say an alter, and you're trying to do some update, don't mix these things. Put them in different transactions so that you don't block it the whole length of the transaction. That is super important. And as I say, there is a log queue in Postgres, and let's understand how it operates. So when a transaction, let's say, it needs to acquire a log. And that log is conflicting with a log that is already held by another transaction, this will enter a log queue. So the default behavior is that if this is waiting log, it will wait indefinitely until this one finishes if you didn't set up log timeout. So imagine like you just, here is a log that is hold, and then I can't really acquire this log because I'm conflicted with this, and I will go back. And then all the operations that comes after will go back in the queue, and it will all cascadingly wait for each other. This will create this cascading impact on your system. It is a bad thing. So to be able to avoid it, you need to make sure, at least for your DDL commands, you need to set log timeout, because then you will avoid this indefinite waiting, which you don't want to end up. It's kind of hard, the queue, how to see this queue. It's really not visible in the pglog system view because we have the system logs view for this, but it's not really visible, this behavior. But you can find it through, there is some function called pg blocking PID, so you can identify which backends are blocking which specific backend. It's not ideal, maybe that could be improved a little bit in my opinion, but this is how it works now. And we will see in an example how it actually looks in real life. But before we go there, the takeaway, it is really important, at least for DDL, you need to set the log timeout because you don't want to wait indefinitely, definitely. But when you set the log timeout, also, again, when you make this decision to set for DDL the log timeout, you will have to also agree to a plan what happens when this timeout error happens. So ideally, either you do rollback or you have to implement a retry logic, because if you just give an error and do nothing, it will probably cause problems in your application. And applications rarely differentiate what comes from database, so you need to make sure that there is some strategy here. Anyway, so let's see the log queue example, how the blocking actually works. So at first, imagine, and the first then, there's a long-running select that is running long. It's just a simple select normally. It looks like really innocent. You don't feel like it will cause anything. Why do I care about my long-running selects? That's why you have to take care of it. Because when you are actually trying to do a schema modification, and if there is a select, because since let's say the second thing I chose, particularly this command, because this actually happened in real life, alter table detach partition, it needs to have a brief access exclusive log. But it can't take, because this select and this access exclusive log, since it conflicts with everything, they conflict. And then, so I put the alter table behind this queue after this select operation. And then I'm trying to do, I don't know, 30, 40 selects, some simple primary lookups, and they will all go back after this alter table detach partition command. So basically, we block everything that comes after this. So first the select needs to finish, and then the alter detach table needs to finish afterwards, after that's done, and then we will actually operate the serving of the select. So basically, there's no concurrent access to this table until all these things finishes. And that's really, really pretty bad. So that's why it's important, especially in the high concurrency environments, you have to make sure that at least for your DDLs, not for every operation perhaps, but for DDLs, you need to have a log timeout enough to prevent this happening. And again, of course, when this happens, as we talk in the takeaway, you need to have a mechanism to handle this gracefully. You have to have a retry logic or rollback or try again, I don't know. And this brings us to our fourth takeaway, because as you remember, the whole thing started with a long-running select. So any long-running query, it can be your monthly, I don't know, report query that runs. And if you don't plan it well with your schema changes, it can cause problems. So you need to first monitor these things and make sure that you don't really have these long-running queries. They can actually cause problems. In one of the problems, basically. Another one, as you see in the MVCC, if you keep this long-running query, it will still keep that version of this rows that we were creating forever. So Wacom will not be able to clean it. You will not get rid of this version unless this is all done. So it's important to make sure you have you monitor these things as well. Okay, now the fun part. Up until now, I know that it was really theoretical, all this talk about this and talk about that. But now we will actually see real queries, and I think that's the fun part. So imagine we are, how to make sure that we do things better, or maybe better for our, performative, less locking. First, very basic tip is that if there is a command that has the concurrent version of the same command, same subcommand, try to use it, because then first it will be if there is a concurrent version, means that you will probably take a lower, less restrictive log. That will probably be that way. And then you make sure that you take these things maybe shorter time. But this doesn't come with also easy, right? Okay, I just use the concurrently, I will not get any locking problems anymore. I'm creating my indexes concurrently, I don't care. It is not correct. So you have to make sure that what happens. So once you choose the concurrently, excuse me, it will definitely take longer to complete than the normal version without concurrently. And it might not actually succeed. So you have to make sure this actually, since it will internally, for concurrently, there will be multiple transactions that Postgres handles in the background. So they will take probably longer, and they might not succeed. So you need to monitor these things. It's not like I set the concurrently and I'm done. You need to monitor what's happening. And if in any case, let's say if there's a failure, there are commands to help you out. Let's say in this detached partition example, if there's a failure in any of the internal steps, you can actually, I don't know, run a finalize command. There are commands like to finalize these steps. So nothing to be scary. It will not cause any issues in that regard, and you will not create any problems, but it will take longer. And another thing is very important. These are not transactional. So you can't really roll back if something goes go wrong. So that's why that is important. You should try using concurrently if you can, but you need to be aware what you are actually deciding here as well. So if there's a half work done somewhere, you need to finish it. It's not transactional, it will take longer. So treat them with care. In the, for example that I used here, alter table, detach partition. If you didn't do concurrently, it will be just like what happens. Without concurrently, let's say there is a partition main table, that is partition we are having, and there is like this the detached table that we are trying to detach that partition. So if we didn't use concurrently, what happens? First one, the root table, the main table, that will get an access exclusive log, means that it actually, it will block all operations, everything, while this detached thing happening. And in the detached table, also you will get an access exclusive log. Again, in the whole this detachment happening, you will not serve anything. There's no reads, nothing, you just block the concurrent access. But in the case that you are doing with concurrently, what happens that internally, to minimize the locking, Postgres will divide into two transactions. In the first transaction, main table this time will not get access exclusive, it will get share update exclusive. So it will still allow the main table to open to be reads. So that's amazing. So you can, but you cannot do like schema changes at that time, right? You can't do add or remove colors. You can't really alter partitions, but you will still provide, so the access is still there. And in the detached table, again, share update exclusive. So you still actually, even from the detaching process, you still actually allow reads. Then once this first transaction finishes, Postgres comes to the second transaction. This time for main table, again, I'm not blocking the access, but for partition this time, a short access exclusive will be needed until this is done. And then there's also an internal check constraint to make sure that the same partitioning rule is enforced. But it is perfect compared to what it is the other way. Otherwise, you will have to block everything. This happened to a customer when I was working in a big company. This was one of the biggest payment systems in the world. And their automation tool forgot to add the concurrent when they were detaching, and they blocked all the access to the main table. That was really chaotic for them. So it looks like simple, but it's really crucial to understand what happens. Okay, now the other strategy. Okay, the first strategy was about concurrently. Second strategy, if there is a way to break down the large operations into smaller, less blocking operations, try to do that. So let's start with the example that I chose here. I am trying to add a not null column with a default value. So what I do in this single command, first one, this command requires an access exclusive log, and it will rewrite the entire table. So if it is a large table, we are looking at maybe a significant downtime, and which we try to avoid, because everything is blocked, no selects are even allowed. It will be whole, the table right, we will have to wait for this. It can take long. So what can we do? We can actually break it into 3 less blocking steps in the second part here. So what am I doing? First, I'm adding a nullable column instead of starting with not null. And then I'm populating any null values with this updates that I wrote here. And actually, you should do this also in batches, because again, remember, you don't want to run transactions too long. So while you do updates, also separate them in the batches. And then after that, I'm adding the not null later. So why do I do this? What is the benefit of it? The first column addition, it is really quick, and it only requires a very brief access exclusive log. So I'm actually shortening the duration of the log that I will have to hold. And the second one, for the data population, when I'm doing the update part, is just a normal row exclusive, means that it actually doesn't block, right? So it is allowing the concurrent operations to happen. And then at the end, it's just like, basically, I managed to separate these things to a less restrictive and short holding log time. So this is really good. And again, as a generic advice as well, when you do this kind of operations, you need to make sure the long contention, what kind of things happening in your system. Sometimes you might need to actually lock the table that you are trying to manipulate on purpose yourself. Okay, but this is not the end. So this is an improvement from what it was before to separate the three things. But can we go further and make sure we can actually optimize this better? Yes. Let's take it from the last comment that we added, right? So the alter table with not null comment, that's the last query that we had. But this is still, it's an improvement. It will not block the writes anymore, but it will still it will still block the writes. It will still long time, but it will not block the reads. So that is an improvement from where we started. But how can we make it a bit better? So you can actually use something called check constraints and use the benefit of check constraints as in like we can add these things as an invalid form. So what I do, I actually again divide this query to more steps. First, I am adding a not valid check constraint, and then I'm validating the constraint as a separate step. Why I do that? Because when I do edit the command as not valid, I only care about the new data that is coming to the table. I don't care about the existing data. I'm not validating that at the same time that I'm creating this. And after that, I am validating the constraint. And this time, I'm not blocking the writes because I'm actually caring about the validation of the existing data. Otherwise, if I do this like as the first way, when I was doing set not null, there we care about the existing data and the new data at the same command. So I'm blocking the new inserts. But the other way around, we actually divide these things so we don't do that. That's why it's really important. And once after all is done, Postgres is also smart, right? When this validation happened, I can drop this check constraint and add the not null column because then it will be like very simple metadata operation. Postgres is saying that, okay, now there's a valid check constraint. I will still take an access exclusive log, but it will be very brief. I know that this is valid and it will be very quick and I'm done with it. So it's really important knowledge. You can do this for many things like adding invalid constraint and then validate later. Okay, so basically the takeaway is that, of course, it takes some expertise to know these things, but it's like very simple and you could already take this with you and try to minimize locking if you can. And good news, Postgres actually is improving. So imagine the last command that we ran, and that was a volatile value, right? The clock timestamp is actually a changing value every time you query it. And this time is almost the same, but instead of like the clock timestamp function that I wrote here, I just have this default one. If you were running an older Postgres version, it will be still trigger a full rewrite for this command. But if you are running in a modern Postgres version, it will be really quick because Postgres is seeing that this is a default value. It's like 1, so I can store it as a metadata. I don't need to rewrite table for this operation. So it will be super minimal looking and super short. But if you are running in the older version, you might actually still getting this full rewrite for the same command. So that's why it's really important to upgrade. If you can upgrade, make sure that you are always running the latest possible version that you can run so that you can lock mechanisms themselves will be improved. There will be more concurrently, almost every release, more concurrently comes with different subcommands. So as you can see here, for example, previously long-running operation might actually become a quick metadata operation. So I know that it's really hard to convince big companies to do upgrades. I know the upgrades are not the easiest things in Postgres. But again, it's these kind of things can be in your hand when you actually propose this to decision makers that why they should actually keep Postgres in modern and upgraded versions. So this is one way to look at it, and I hope all the companies can get this message sooner or later. And this is the last bit of the talk. We basically finished the regular Postgres part, and now we will learn a little bit about the tool that I'm working on. It is called pgroll, and it is kind of like a sushi roll. That was like the joke level that we have. And so what was the motivation? As you can see, handling this schema migrations can get complicated. So we built a tool that is open source that helps people to actually solve these problems. And some of the mechanisms that we talked are already implemented in the tooling itself. So what we do, the main way that I think it works is that we keep the multiple schema versions. So once you have, let's say you have the old schema or the current schema, let's say, and then the schema that you are trying to do the upgrades into. So your client applications can have different versions, let's say V1 and V2, and we can serve them both at the same time. So you can do a rolling upgrade while you do the schema changes. And if things don't go well, you can just roll back. There are like different tooling for it, not many of them open source, but they usually consider rollback as an like advanced feature. So even if you are using this tooling, you can't really roll back easily. But for us, all the features are free and available, and it is exclusively Postgres, which means that you can actually take all this core Postgres knowledge and focus on the Postgres-related solutions. I think that's kind of where this tool differentiates from the other tools. And we also have like handle the data backfilling. This is something that you have to do if you want to do zero downtime, graceful upgrades of your schema. You have to fill like the data back and forth, because if you are keeping the, let's say we have this table, we are trying to add a column or a constraint, and in the other version of the older version, you don't have this constraint. So if you are writing to, if you are still serving the old versions of the application, they will keep writing this data without actually fulfilling this constraint. So what we do, we actually have triggers up and down way. So we do like, if this old data comes, we actually convert them in the way that you want it to be converted. And if there's a new data, we'll actually also go back to the old column, or let's say without the constraint, you'll keep them both ways updated. The way that, since we do handle it all in the database layer, so you actually take this logic, all the migration logic from the application to the database, so you don't actually go back and forth between application logic and database logic. It's purely in database, you can handle the database schema changes. And yeah, how does it work? We actually have higher level operations, so instead of writing the SQL directly yourself, you can just do it like add column, I don't know, add this constraint and something. And then it will actually convert to the SQL kind of logic, and it separates them in a way that it will stop getting the strong logs. It will help with the log timeout. It has the retrial logic already implemented. You can actually configure the batch size and delay the batch that you are making while you do this data backfilling and so on. So it is kind of smarter, and make sure that you can do blue-green type of deployments without any disruption to your system. And this is how it looks normally. And we do now migrations as default to YAML migrations, but you can actually do with JSON too. That was the beginning of the project. And you can also just write SQL if you want to just do it that way. And there is something that we utilize. It's called a software pattern, expand and contract. It's kind of hard to say, but what it does do that we actually adding temporary columns to the physical table that we are trying to work on. We are backfilling the data and transforming in the background. And this, we have different views to show different version of the same table, basically. One version of the view sees the older way of looking, and the other one sees the what newer version of the application wants to see. And then once we don't need this anymore, we finish the migration, we just delete the temporary columns and temporary things that we added. It usually looks like this. So the application version 1, application version 2 is the new one. At some point in the middle is the red block. They all both live simultaneously, and when you finish the rolling upgrade, you finalize the migration, and then you have with one migration. But you can keep this red state as long as you test, you try, and then once you're happy, either you can go back. If you're not happy, you can go roll back to this one version. Or if you're happy, you can just complete it. And again, as I said, we just handle it with different views, how we show the changes. And applications, applications can select its version. We utilize a search path. So it actually goes through the different schema through this search path, and that schema has a different version of the view. So that's how we operate it. And yeah, you can control the batch size, as I say, for the backfilling, and you can actually write this up and down triggers, so you can manipulate the data as you want. And yeah, pretty much like this. And important thing that we have this try log logic already built in. So if there's a timeout, we actually know what to do with it. And all the alter tables are actually prefixed with the set log timeout command, basically. Yeah, I think benefits are clear. Rollback is easy because this is something people usually, what we see is that everybody has this like migration scripts, and they have different versions. They keep the versions of the scripts, and they also have the rollback scripts. And it's not really easy. I mean, that's how we were doing before all these things existed. And that's how mainly people with big companies also do. They have like this migration playbooks that you need to do this step and that step, change the code now, switch the application then, and so it's really lengthy process, and that's why I notice some people don't want to do the modification and they avoid dropping columns altogether. They just something called roll forward instead of, because they can't really do rollbacks. So this kind of makes things more manageable for those people, and maybe it might be helpful for you. And if you try it out, please let me know. I would like to get feedback, and yeah, contributions are always welcome, of course. We have like this repository. If you want to check where the repository is, this is the QR code for it. And we also write blogs about stuff. We are part of Planet Postgres. If you're not following that kind of blog aggregator, we keep writing what we find with these open source projects in there. And merci beaucoup.
Thank you very much. We take time for one question. Any question?
Hi, thank you very much. Just quick question. How do locks and streaming replication work? Say you're doing an alter table on your primary. Can you still read data from the table on the replica?
Like how the Postgres operates with replication, that's like if you are doing the main operation in the primary, that's where the locking behavior happens. So if you're not blocking that table, and replication will still continue. So you don't really stop the replication from what's happening, if that's the question.
Thank you.
You're welcome.
Thank you.